everybody. I'm going to do another example problem for you. This was one I've made up myself, and it's in honor of my dearly departed mother, who was not much of a scientist, but did make one scientific claim that I can recall in my entire life, and that was that if my hot cocoa was too hot, that I could cool it faster by leaving a spoon sitting in it like this. So I'm going to demonstrate all this with this sweet new Star Wars mug that one of my grad students gave me recently, and this spoon. So I've taken some dimensions from this, and please imagine that it's full of hot cocoa. Please bear with me as I don't know how to pause this recording, so there's going to be some messing around. So I've taken the dimensions of this so-called fin, and I'm going to use some other numbers that make sense for this hot cocoa problem. So here we go. Let me see if I can set this up on the paper. Oh, upside down, but I can fix that. There we go. Okay. Okay, so I'm going to, I've taken some very rough measurements of this spoon and found that it's a thickness, the fin, I'll say in quotes, the fin is 0.5 centimeters wide, 1.5 millimeters thick, and 8 centimeters long. So in other words, this is this dimension here, this dimension here, and like this. Hope that makes sense. It's sitting inside a cocoa, 90 degrees C, just below boiling. If it were hotter than that, it'd be boiling. If it were cooler than that, then I wouldn't need the spoon to cool it down. So it's sticking up out of a cup of cocoa like this, and 90 degrees C in here. We're going to say that this cup, and I'm not going to use this information for the first part of the problem, but let's say that the cup is 7 centimeters in diameter. The cocoa is 6 centimeters deep, and yeah, I'll use that information later on to compare the heat loss through the fin to the heat loss through the sides of the cup. We choose 5 watts per meter squared Kelvin here. This is a typical natural convection in air number. So that's the convection that's happening off the fin out here. We could come back and revisit this in a couple weeks and see if we still like that number or not. Stainless steel, which your silverware is made out of, is about 15 watts per meter Kelvin. Might be interesting for you to go and look up the silver thermal conductivity and how much more you could burn yourself on a silver spoon than one made out of stainless. Huge difference. Outside the cup, out here, oops, try that again, T infinity is equal to 20 degrees C. So we'll use that when we're making that comparison. So I need to make a cross-sectional area of the fin, and that is going to be 0.0015, 1.5 millimeters times 0.005 times, or equals, 7.5 times 10 to the negative 6 meters squared. That's the cross-sectional area of the fin. That's this area right here. Okay, in addition, I need the perimeter of the fin, and that is 2 times 0.0015 plus 2 times 0.005, and that's equal to 0.013 meters. The so-called fin parameter, which you'll see on the table of all the different fin equations, capital M, is equal to the square root of h p k cross-sectional area times the base theta. Remember, theta is the... So we're going to assume here that the base of the fin, or this is the definition of theta, and T infinity is the air temperature out here because that's what the fin is convecting to. The base temperature of the fin is 70 because we're going to assume that the base of the fin is at the same temperature as the cocoa, and then minus the 20 degrees T infinity. Okay, so if I put all these numbers in here, capital M is equal to the square root of 5 watts per meter squared Kelvin times 0.013 meters times 15 watts per meter Kelvin times 7.5 times 10 to the negative 6 meters squared times 70 degrees C. And that is equal to 0.189 watts. Capital M has units of watts. I also need the small m, which is the square root of h times the perimeter over KAC, which is equal to 5 watts per meter squared Kelvin times 0.013 meters over 15 watts per meter Kelvin times 7.5 times 10 negative 6 meters squared, all that square root. And that's equal to 0.24 meters to the negative 1. Whoops. There we go. I am also going to need the quantity h over mk. Comes up a lot, and that is 5 watts per meter squared Kelvin over 0.24 m to the negative 1 meters to the negative 1 times 15 watts per meter Kelvin. And I've checked all these units, they're all working out okay. This is a dimensionless number, it's 1.388. So that means that the sine, or the hyperbolic sine, of ML is equal to 0.0192, and the hyperbolic cosine of ML is equal to 1. And the reason I want that is that my heat transfer total from the fin is equal to from the table 3.4 in your book, it is equal to capital M times sine, hyperbolic sine of ML plus h over mk times hyperbolic cosine of ML over hyperbolic sine, or cosine, ML plus h over mk times hyperbolic sine of ML. This is, of course, the assuming nothing. This is, no assumption here. This is convection off the tip, which is the most rigorous answer we can get. So I've already computed my sine and my cosine here. I've got capital M up here. I've got small m down there. So now I can just fill in all these numbers and finish the problem. So let me do that. So Q is equal to 0.189, which is capital M, times 0.0192 plus 1.388 times 1 all over 1 plus 1.388 times 0.0192, and that is all equal to 1.37 watts of heat that we're losing through our fin all the time, or at least when it's hot. So I came to that answer, and I was proud of myself. Said I can use fin to analyze this, but now I need to ask the question: is that a lot? And whenever you ask is something a lot, you have to answer the question: is it a lot compared to what? And in this case, compared to what, the best what I could think of is how much heat is going through the walls of the cup all the time anyway. What would have happened if you hadn't put the spoon in there? So here is my cup. It's a piece of ceramic. It's got cocoa inside, and that is 90 degrees C. 90 degrees C, and H is equal to 800. So this is a liquid H on the inside. I think I might have misstated the H that was 5 was for the air on the outside of the fin previously. Again, these are just numbers I'm assuming. You could argue with these. And on the inside, I'm going to say it's 20 degrees, or I'm saying on the outside it's 20 degrees C, and I've already said that it's the H on the outside for the air is 5 watts per meter squared Kelvin. And let's say that this cup is made of fused silica. And I found in the tables in the back of the book that for that, K is equal to 1.38 watts per meter Kelvin. So this is a thermoresistor network problem. And my total resistance is equal to 1 over H on the inside plus L over K plus 1 over H on the outside. So what I've done here, some of you might be crying foul and saying, "Hey, this thing's round." Well, I'm only treating the sidewall, and I'm not really. I'm taking I'm taking advantage of the fact that the diameter of this thing is large compared to its thickness, so it's not going to act much differently than a plain wall. The fact that this is curved won't have much to do with it. And also, please keep in mind that this is a swag to begin with. So my R total then is equal to 1.25 times 10 to the negative 3 plus 3.62 times 10 to the negative 3 plus 2 times 10 to the negative 1. So this is our big player here. This is our big resistance, and it's the only one that's really, this is going to dominate the problem. And when I put all that together, and I note that Q prime prime is equal to T minus T infinity over R prime prime total, I get that my heat flux is equal to 350 watts per meter squared. I notice that this is a flux. I need to convert that to a heat rate by multiplying by the area, and that's equal to pi dL plus pi d squared over 4, which ends up being equal to 1.7 times 10 to the negative 2 meters squared, and therefore my Q is equal to 6 watts. So my conclusion based on this, and assuming none of you find anything wrong with my arithmetic, which you've proven to be very good at, is that this number is quite a bit larger than what we're getting from the fin. So the fin may be helping a small amount, but I think you could probably get further ahead simply by stirring the stuff than it is by just simply cooling because of the fin sitting in there. So unfortunately, sorry Mom, I think you were wrong about this. But then maybe she would tell me that my H's aren't really valid. So thanks, and hope that this was helpful.